ちょっと危ないので、注意ぐらい。
そうですね。とりあえず、ラジオテープで止めましょう。追加と注意がいらっしゃいますけど。
はい。
そんな研究会で。はい。プログラムってなんとなく
いや、まだ通ってないです。
年度末でね、出張書籍を早く出せとか言う。
まあ、
それ事情はわかるんだけど、
じゃあ、そう。
なんとなくね、公開できるようなものでなかった。それと、
いや、まだ全然、
やろう。
まあ、やばい。すみません。確かに、でも、ちょっと、そうそう、
全部行くっていうのもいいけど、
先生、
にしかいけないとか言ってに、ここら辺っていうのは。
机前にして危ないものですから。そうですね。はい、養生しております。
近日中に、作る。特にダブルの公演も行ったりとか、何かあります？
あれでしょう。かなりパード来なくなった。
来れなくなった。2年前から今度作ります。別前に聞いた。でも、宿泊券なかったし。
広がったのにしまって。はい。
はい。はい。出かけはないと信じて。
今何時？もうこの1分前ぐらい。
多いね。
一応宣言してたんだ。ちょうど50分やってたんで。Good morning. Yeah, Alexei not here, but I think getting time to the second day's talk. Just arriving. Alexei, we start here. Okay, let's start the morning session of the second day. The first speaker is Professor Lutz from the University of Munich. Not the Munich.
First of all, I would like to say, when I was on the invitation, on the subject I will talk about is a bit more in direction of algebra. So let me start with a short motivation. With you, we have two finite dimensional algebras in a prime. So I always work over algebraic those here. I mean, there's a version of this theory also for non-algebraically closed fields, but then it's more difficult. So these are three-dimensional algebras. And then what I also usually consider are some algebraic varieties, which always are smooth and protected. And what I want is, I have the corresponding derived category or the corresponding immediate category, which is, for example, the category of modules or Fourier sheaves on it. And I always assume it has the full exceptions. So for algebraic varieties, this is a rather restrictive assumption. But for algebras, there are large classes of algebras, for example, was which allow such a full exceptionist. And a general question, which is, I think, very difficult to answer, is when are two such algebras derived equivalents? So I always work with a bounded derived here. Or the other question is, when is such an algebra derived equivalent to the coherent sheet on the latest graph? So you would like to decide for two given algebras or for, for two finite dimensional algebras or for the wide variety, whether there are algebras which are derived equivalent to this. So, and this question has, I mean, this is far from possible to answer, but this has two aspects. One is the discrete aspect in the Grothendieck group. And with Grothendieck group, I always mean Grothendieck group together with the Euler form. So what I always need is that we have an Euler form, and full exceptional sequence, let's say of length n, says that the Grothendieck group is isomorphic to the free Euclidean group. Set to the n, where n is the length of the sequence. And then it has some non-discrete aspect, but for this you need varieties of algebras. So if, let's say, you know that on the level of the Grothendieck group you get an isomorphism in the derived category, then you may ask, I mean, do the algebras themselves actually have such an isomorphism? And this is a much harder question. So I want to look to this discrete question today. And the way I treat this is a very elementary and very, we discussed also about is it really not related. So let's start with a full exceptional sequence. I assume you all have this means. And then we can associate with that the full exceptional sequence the corresponding Carter matrix. And so this, the general assumption is that we have such a thing. So the order characteristic is a finite number, I look at it as a number. And by assumption of full exceptional, this means we have one of the principal diagonal, we have zeros up below, and upstairs we have the order characteristic of the I. So this I call the Carter matrix. In case the algebra is directed and you take the projective modules, this in fact is the Carter matrix. But so let's say this is the Carter matrix of the full exceptions sequence. And now the way I look to the problem is the following. I define now the Carter matrix with variables. So I take the same matrix, but instead of taking the order characteristics of the full exception sequence, I take variables. So this works in a ring, which I call I. This is the integral polynomial ring of variable xij, where 1 is less or equal to I, is less or equal to j, is less or equal to L. Can you read this? And because sometimes these indices are in the wrong direction, I identify this ring also with the following ring. So I take all variables xij, where 1 not necessarily ordered, and then I factor out by xij equals xji, and on the principal diagonal I put the entries 1. So this is just for convenience. So this is a matrix. So C is an n cross n matrix over the ring R. So now we get several actions on this ring. So first, the actions usually are defined on epsilon on the exception sequence, but then they are also defined on the corresponding color matrix, but then also on the generic color matrix, and then also on the ring I. We give some examples. I mean, maybe the simplest example to start with is we make a shift. So if you put a shift here, so let's say epsilon prime is E1 up to I minus 1, and then with EI I form a shift. Then I get the corresponding action. So this is the shift at the I position. Let me call this maybe EI times epsilon. And this gives at what you do to the n action on the ring. And so x, let's say LK, left by this element to the same element if LK differs from I, left to minus x again if L equals I or A. Just have a fine action. And this gives an action on the ring. So there are several of these actions. I mean, the next one is the breakthrough action, EMX. Maybe let me explain this again on the level of the exception sequence. So you start with an exception sequence, and then you put again the position I, but then you, so to say, you can, I mean, you transpose these two elements. And replace one by the left notation with respect to the previous one. Where the left notation you can also understand as follows. So you take the generic home from EI plus 1, and then you tender with EI, and you get a lateral length EI plus 1, and then you do this over all degrees. So in principle, you can also put here minus k, you can put k. So you get the canonical map, and you get a distinguished triangle. So there are several ways to define this new object. You can also define it in the way whenever you take this sequence, then there's a unique object so that you get a full exception sequence in this position here. I mean, maybe in the example, I mean, it's sufficient to do it for 3 elements. So what does the left rotation at the first position mean on the level of the cover matrix? I mean, the columns from here to here are the same as before. So you get x1, 2. Then you see the homes from this place to the other ones are now the homes from this place to the other one. So get here x 1, 3. And then here you take x1, 2 times x1, 3 minus x2, 3. So in principle, so to say, you interchange some elements, and one takes the same degree, but one gets the degree 2. So this gives the action on the ring Rn. Maybe I don't want to describe for detail what this leads to in Dn action on R. And there's another action which
There's a question.
Excuse me, please. Does this action preserve the ring structure? So what multiplication is there of this ring?
is defined on the chapter. I mean, because these are free elements, so when I do any, I mean, that's why I really take the generic Carter matrix in this sense. I define everything is defined, so to say, on the generic.
This ring, we don't use the matrix structure at all. It's just the ring of polynomials with integral.
Oh, yes, yes.
But not,
Not a
not
polynomial.
polynomial. It's just a direct sum of use.
The polynomial ring in the entries of the Carter matrix. And then it says the 4 actions, sorry. Okay, so I have this. The action of Z module n, which just sends xij to xi plus 1 j plus 1. What modulo that's clear. And so it makes sense if you look to this definition. So this essentially means, I mean, if you shift your elements down here along the diagonal, and this element goes to this place, and this element goes to -1. Now we split just in each position by 1. And okay. It doesn't matter because the inverse action is it in the other direction. So we have these actions, and maybe let me explain what the invariants of this ring under the shift actions are. So this is just plus or minus, but this already gives you some kind of strong position. Namely, this ring is generated by monomials, which comes from the symmetric group, where I define x sigma to be the monomial 1, sigma 1, x2, sigma 2, and so on up to xn. So in principle, it's sufficient to take here cycles. So that's why I call it also cycle ring, because it's generated by cycles, which means, so to say, that each variable appears twice. Yeah? So if one appears here, then at another position it must appear again. And all these elements where you have the same entry, you send by Z1, so you can forget about them. And so whenever you have a cycle, let's say like this, let's say 1, 3, 5, 6, 7, then you get a monomial which is x1, 3, x3, 5, x5, 6, and so on. So you can do the same game also for graphs. So if graph gamma is a subgraph of the full graph within vertices, and you can do a similar thing. You just the product over all edges in the graph, and then you take x, I, j, where the edge goes from I.
Answering. In your formula, the second one is x2 something.
x2, yeah.
Right, and on the
Sigma
x3
and sigma n.
and there. Yes, but on the in this. Yes, in the film,
3, 3, 5, 6, 6, 7, 7.
it should be x2 in there.
Yes.
Then you look on this polynomial.
This one.
Yes, the second one. It contradicts this one.
This one.
Yes.
This is just the notation of a cycle. So the cycle is 1 is mapped to 3, 3 is mapped to 5, 5 is.
Yes, I understand, but still you have x2 sigma 2.
But 2 is fixed. So xii is 1. So if I fix an element, then I put it 1. So x2 is 1.
Sigma 2 is 2.
Yes.
You made cycle only for
1 is mapped to 3.
okay.
5.
All right. It's cool.
So you just think about this as a graph. Yeah? So I mean, you have these two notations. I mean, you can either do it for the computation or you can do it for the graph. So, and then the first problem is, but it puzzled me since a very, very long time, and I couldn't solve it. Describe the invariants under the break corrections. I should give you maybe 2 examples. So for n equals 3, there's a very famous equation, the so-called Markov equation, which first appeared for coherent sheaves on P2. And then later I also used it for some cluster rotations. And it turns out that this equation, which is x12 to the square plus x13 to the square plus x23 to the square minus x12, x13, x23 is essentially the only invariant. So let me call this here for later use also F1. And so R3, if you take the ring R3 and you pick the E3 invariance, then you can explicitly show this polynomial ring of this Markov. Because this generalizes, maybe I come back to this problem later, to higher ones. But there's another example which may be important for n equals 4. We have a polynomial which I call G. And this is, I mean, essentially, so to say, you take for the graphs, you take all dimers for 4 vertices. So what are the dimers for 4 vertices? And you can connect in this way, you can connect in this way, you can connect in this way. So this polynomial has 3 terms. And the first term is x12, x34. And then you have x14, x23. And then you have a minus sign because you have a crossing here. So the crossing means you get a minus sign. And it's x13, x24. So if you know this polynomial, I mean, this is just a Pfaffian, the antisymmetric. So this also is no meaning. But unfortunately, I could solve it only step by step. So I solved it, I think, until 5, and then I gave up because there's no, I didn't found any way to utilize this. And then I found a way to go around this problem by introducing another notion. which is close to this question, but it's slightly different. And these are the polynomial invariants. So this was the first one. So now we do something with strange. If I have such a polynomial with ring Rn, then I define what is the evaluation of the exception sequence in this polynomial. And what I do is I plug in the order term with this definition. So for xij, just put in natural numbers, and this is the order term. And then I say f is a polynomial invariant. If for all exception sequences in the triangulated or in the repeating category, so it's anyway for any abelian or triangulated category, the value of so f of epsilon only depends on the category. So you can, in general, you can have lots of one exception sequences. Maybe I should say the n is now fixed. So I only consider triangulated categories which have full exception sequences of length n. And then I consider polynomial in this ring Rn. Then I can evaluate it as an exception sequence. And I can ask for those polynomials where the value does not depend on the choice of the exception sequence. So it gives an invariant of the category. What?
Here you fix the gate.
Oh, I do it for all categories. I do it for all. I take any category which admits a full exception sequence of an example. So there are some categories which have only finitely many Cartan matrices or even finitely many full exception
But you
sequences.
fixed. I mean, there's definition, you fixed the gate. Then what's the difference? This.
I will see, there's a difference. So this polynomial P is not a polynomial.
This expression is not in the algebra, which is generated by the coefficients, I guess, right? Yeah. And that was also-
Here I take D. When I can separate.
All your geometrical actions should preserve the. All your geometrical actions should preserve the parent, because parent is important. You choose two for each section, right? And then you have the Cartan matrix, but you have the action of like great hoops.
Yes.
Yeah, so each action should preserve
Sure.
the parent.
So in particular, each polynomial each polynomial invariant is invariant on the brain. So if it's so let me finish. So I define R. This is the set of all polynomial invariants. So I define this as and if it's a polynomial invariant, then it's preserved under the breakpoint action, so I get an inclusion. Of the invariant ring under the breakpoint. Is this what you mean?
usually you have like a Cosmonic connection. And the Cosmonic connection, so you get horizontal parallel transportation. And those parallel transportation should preserve the parallel. And then you get the polynomial invariance in your abstract system. So parallel is important.
This I don't understand. I mean, I'm working for algebra, so I mean, so
It's not even parallel structure, right?
Maybe one remark. Lutz,
yes.
the answer to the first problem, I think, was written in my paper.
Completely.
Hmm?
Completely.
I think so, yeah. About the symplectic group weight.
The answer to the second question. This is then made also in your paper, construction of here. So what I do is I take the determinant of the Coxeter transformation. So I take the characteristic polynomial of the Coxeter transformation. The Coxeter transformation is defined as the Carter matrix inverse times the transpose. And then so if I take the characteristic polynomial, then I can decompose it into fi I equals 0 to n. And then to avoid constants, I think the constant is always n over I. So I define this in this way. I define polynomials fi in my ring Rn. Without constant terms. And they are all of degree n. So why are they of degree n? I mean, because this is the same thing as the determinant of C minus C transpose minus C times C. But this is also the same as the determinant of, I mean, you can transpose it again. So you can take C minus. And on that's matrix which has linear entries, so the determinant has degree n. So all these degrees of the fi is that equal to n. But it turns out that in fact you get inequality. So let me give some examples maybe. The easiest to determine polynomials is the one which you can generalize as follows. So you take I1 is less than I2 is less than IR. And then you take the monomial which corresponds to the cycle. So you take xi1, I2, xi2, I3, 1 for xi. Minus 1 IR. Then you also take x and you put a minus sign here, depending on the length. So this is So altogether you get n on target invariance. And they are all algebraically independent. And they are all of degree. So in the question is, I mean, does this completely describe the ring of polynomial invariants? We also say something on this Potsdam transformation here. So what it turns out is that if lambda is an eigenvalue of the Coxeter transformation, then it turns out that also lambda bar, lambda inverse, and lambda bar inverse are eigenvalues. So the eigenvalues come, so to say, in different types. So there can be plus minus 1. Then there can be a real eigenvalue, so where lambda equals lambda bar. So here you have maybe one eigenvalue, here you have always 2 because the inverse. And lambda is unequal to minus 2. Then you can have lambda inverse is the same as the conjugate, so it's on the unit circle. If the absolute value is 1, then you also have pairs, and then you can have the remaining case where you have 4 different eigenvalues. So this is, I mean, because this is always even, so this says if n is odd, then you always have, it can even prove that you always have one eigenvalue equals 1. So in your case, I mean, you must have one of the first type. You check directly that there must be at least one eigenvalue of the type. And then you have these other types. But for the other types, I mean, it's an open problem. I mean, how they distribute. So I think there's no review now. When, how often this type occurs, how often this type occurs, how often this type. Also, if you take an exceptional sequence, then you get these eigenvalues. But the question is which type of these eigenvalues really occurs. I mean, so for example, if you have a representation finite algebra, then you know that the only this type can occur. So they are all on the unit circle. For example, this type is even difficult to construct as far, you know. So it's not so clear how you get. For this type, you can use tame algebras or certain type of algebras, but in this type here, it's not clear for which algebras you have this 4 couple of right. transformation is preserves the form. So in particular, it's the orthogonal axis. Yes. Orthogonal axis Charles on the unit circle.
The matrix is not symmetric.
Preserves.
Preserves preserves non-symmetric bilinear.
Serialization. If that is not degenerate, then it's orthogonal. All that's invariance. Yes. This is certainly wrong. I mean, if you take a hereditary algebra, which is a file type, then you never have. When you have a lot of real eigenvalues larger than one. You cannot. Maybe it will be degenerate. Maybe the symmetric form may be degenerate.
Even if it's no.
Yeah, that's okay.
It's not positive definite.
No, positive. No. Okay.
Can you show it's a symmetric transformation? Symmetric, yeah, symmetric geometry.
I'm just coming from algebra side, so I'm sorry.
You can show it's a symmetrical matrix, and then it's clear what's eigenvalue of this matrix. It also looks like this. Because you have the power. To do some real structure.
Yes. Symmetric.
And then may I ask also stupid question? Do you have really the example of this eigenvalue with 4 roots?
I once constructed an example by the computer, but I cannot explain it. So there are examples like this.
In my experience of root system, even not positive, definite, indefinite, many cases, all cases in my experience is either the 1 or 2. In the fourth case, I haven't seen.
I see. Yeah, I think it's rare. So it's not known, so to say. We only found them by computer experiments. So for large algebras and large Carter matrices, you can have this, but I have no explanation of this. So the distribution is completely open.
Can I get some data of that example?
Yeah, I mean, this was really by random matrices.
Something for discussion after the talk.
Okay, so
So now we call the composition. So assume you are given a Carter matrix. Then you can realize C by quasi hereditary. So what is quite simple is, I mean, if you have a Carter matrix where all these entries here are greater or equal to 0, then this is easy to realize. By hereditary algebra installations or path algebra installations. But if you want negative entries, one needs quasi hereditary algebra. So there's a special kind of algebras where the positive the same way you can realize by a directed figure, maybe with multiple arrows, and putting out some relations. And then in the quasi-hereditary case, you also take arrows in the backwards direction. And essentially, I mean, this gives plus signs, and these elements give minus signs. And then you have the so-called standard modules, and they always form in full exceptions.
You have some relation between Cartman matrix of this quasi-hereditary and of these two pieces. If you matrices with these two pieces.
You can sort of say produce plus signs in this way, and then if you need minus signs, then you add sufficiently many of the backwards directions, and then you can make it smaller and smaller and smaller again.
And you should make quasi-hereditary algebra, so you should put some.
Yeah.
I understand, but you should have relations, right?
Sure. So you this way, the project modules over this one become the delta modules over the quasi-hereditary. There's a unique effect. There's essentially a unique fading. So you put so many relations, so to say, that you can build your projected modules by projected modules in this direction. So,
Okay.
Then I also should note that put it if X is an algebraic variety, then all the eigenvalues are either plus one or all eigenvalues are minus one. So there is the value of the polynomial invariance then is uniquely determined just by the property we have in the algebraic variety. So F1 is defined just by the dimensions of the varieties. So maybe let me give some examples to show you how this works. So maybe we take 4 algebras here. We take n equals 4. And we would like to decide whether they are the right equivalent or not. So we first write down the cover matrix.
What is the difference between the first one and the third? Do you have some relation?
So we have two polynomial invariants. One is F1, which is the sum of the xij squared minus the sum of the xij, xjk, xik. And then we have an additional term, x12, x23, x34, x14. And the other one is the g, but we have to take the square. The square, which is this x12, x34 minus x13, x34 plus x14, x33. So let's compute maybe a fun here. So what you do is you take all the squares of the entries, so which is 6. Then you take all these triangles here, therefore, and then you have one last term, x1, x2, x3, and so on. So this times this times this times this. This is plus 1, so you get this 3. And for the G, you take this times this, plus this times this, minus this times this, you get a 1. Here you can compute again, so you get 5. Then you have minus 2, so you get again 3. And for G, you get now 0. So here you have 4 minus 1. And on the other side 0, then you get 3 again. But for G, you get this times this, and the other. So G. The last one is 5 plus 4. Then you subtract 2 from another 4. And you add another 2. So 2 and 4 cancels out, so you get 5. So what you see is that the polynomial invariants are only the same for these two cases here. So these are the only cases where you can get derived equivalence. And in fact, this is a kind of partial duality to this. Yeah, it's not directly partial duality. Partial duality would be have another stereo relation here. But if you change the direction of this arrow, then you see it's a variant of partial duality. But these cannot be derived equivalent even if they are representation finite. And this is the same example which also cannot be derived. So the question is now, I mean, what these polynomial invariants decide. And I think from the construction you can see that knowing the polynomial invariant is the same thing as knowing the eigenvalues of the Coxeter transformation. So if you know fi of epsilon for I equals 1 to m, this is equivalent to the set of eigenvalues of the Coxeter transformation. But this is equivalent to know the Coxeter transformation of conjugation. If the eigenvalues are pairwise. And then knowing the Coxeter transformation, because the Cartan matrix is upper triangular, you can even recover the Cartan matrix from Coxeter transformation. So this is equivalent to know what the group is anyway set to the n, get a Euler form up to basic. The theorem is so the ring of all polynomial invariants is the integral ring over its polynomials f1 up to fm. So they generate free or polynomial invariants. And this coincides either with the string of great invariants. So I think this is already from Hille. If n is odd, and if it's so to say then the ring of great invariance is just almost the same ring, but instead of the last one, we take the G. And the G square is then polynomial invariance. So these two rings are almost the same, except that for the great invariance, you have one polynomial of degree and a half. So all other polynomials are of degree n, and the G is of degree and a half. And the G you can construct explicitly. I mean, either you can take n, or you can construct it as the sum over all dimers. This is take xd, and with the sign, which is the crossing number of the dimer. So this is the same thing as Kaplan. Or this is the same thing as the determinant of the antisymmetrizer, C minus C transpose. And then you have to take the square root. So there exists a square root of the determinant of the antisymmetric matrix. Yeah, so I think I stop here. Thank you for your attention.
Thank you very much. So is any question or comment or whatever? By the way, I forgot to ask, may I go back? The factor element is automatically semi-simple, or it could be some Jordan block?
No, this is, I mean, in particular for algebraic varieties, it's not semi-simple. But it's, so to say, in the generic case, it's semi-simple. But if you, for example, have an algebraic variety, then it depends on the intersection structure of the variety.
Can you predict how this block appears? Jordan block.
Yeah, for example, for surfaces, you can have only a small block because the intersection of two divisors is already a point. And there's also an example of the tame algebras. You also can have non-semi-simple. I mean, generically, it's semi-simple, you are right. But it's not so clear what generic means. Yeah, so this is the problem. So I try to compute the discriminant of the matrix. So it should be in this ring the Bn invariance. But I can do it only in small degrees, so I don't know what the general formula in general is. So the discriminant should decide on whether it's semi-simple or not. So I think whenever you have the same eigenvalues and they are 1 or minus 1, then it's not semi-simple.
Yeah, one is often make blocks. I agree.
But for the others, I have no example. So I have not a single example where two eigenvalues which are not plus minus 1 are the same. Yeah, this is very mysterious.
Well, I found also this very, very interesting, very mysterious. Yeah. More questions. Let's thank the speaker again. We did
I'm sorry. So I know that you constructed this invariant.
Yes, exactly the same answer.
But you explicitly say that the